All right, we found the good JSON line. Maybe good, we'll see. Next, we're gonna find the best line. And again, there's a couple ways of doing that. The most common is called the least squares regression line, which means we essentially minimize the square of the distance between our approximation and the point, and specifically the vertical distance. That's not super important for this class, but there you go, a little freebie. So again, the instructions are in the notes if you want to follow the instructions exactly, but I'll just show you how to do it as well. So I'm going to get rid of these, my other line. We can draw that one later. Let's just start over just to keep things not cluttered. We can add it in later to compare my line with the best line. What we're going to do is notice our table. This is called x1 and y1. We're going to use those variables, y1, and instead of an equal sign, we're going to use the tilde, which is shift apostrophe on the top left of your keyboard. And x, we're going to write x1, press tab to get out of the subscript, plus b. And what this is going to do is this automatically generates the best fit. All right, this looks pretty similar, right? This looks pretty close to my line. Let's see what its values are. Okay, so their slope was about 1.143. Let's write that down, okay? Their slope, so they have c equals, let's start with a b value, b plus mx. B is 30.281. Having some real issues tabbing over. 30.281 plus m, which is 1.143. We use 3 decimal places here. You can just use 3 or 4 depending on what the problem specifies. Times t. Right, ours earlier was just 32, pretty close. 1.1, very close. So their y-intercept, their starting value is actually a little higher than mine, or a little lower than mine, which I'm actually surprised that the slope was so close, but the b value is a little off. So yeah, I mean, that's pretty close. I'm gonna say pretty close. And in fact, if we do both of them right next to each other, right? If we put that other one right back up, y equals, or again, we want to be, right? C equals 1.1, let's say 32 plus 1.1 times t. Okay, this green line and the pink line are pretty close, right? They're modeling the same data for sure. We did okay. The purple one was quicker to generate though, because we did have a computer. So let's use this data to predict the temperature if we count 28 chirps in 15 seconds. We're going to now use this linear model. We have a linear model. Now we're going to use it to predict temperature. All right, so when is the temperature, or find the temperature, if we count 28 chirps in 15 seconds? So that's going to be a C value of 28. Do I have my C and my T backwards? I do. C is the input. T is the output. So it really should be T here and C here. And likewise, the T and C should be switched. That's going to make letter B a lot easier. Okay. Hopefully you noticed that, and hopefully you were screaming at me in the monitor. Okay. All right. So if C is 28, what does T have to be? Well, we know T is 30.281 plus 1.143 times C. All we have to do is type this into a calculator, and we can get our approximation. All right, what is our temperature going to be? Let's type it in. All right, so our answer is going to be 30.28. Oh, I have it right here. We're just plugging in 28. 30.281, 28 times 1.143, 62.285. Or you could approximate it if you want, about 62 degrees Fahrenheit. And if we plot this information, right, 28 chirps, 62 degrees Fahrenheit, 28 chirps, 62 degrees Fahrenheit, that's the blue point. That's our approximation. We're using the line to approximate the data. I rounded a little bit. It should be 62.285. So when we approximate with the line, we're getting a point on the line. All these approximations that we use this linear model for are giving us the value on that line. That's how the line works. All right. So there we go. And likewise, if we know it's going to be 75 degrees tomorrow, how many chirps would we expect in a minute? So first, right? First find C when it's 75 degrees Fahrenheit. And then C is going to be how many chirps are in 15 seconds. Then we're going to multiply by 4. All right, it's not supposed to necessarily be a trick question. It just wants you to always be thinking. All right. So let's write down that we need to do this because I'm probably going to forget. So don't forget. Maybe you even write. Forget this, Jason. Or maybe you include your name here. I'm going to include my name. You can put yours. And that's just because this problem is trying to get you. So we know that T is 75, and that is equal to 30.281 plus 1.143 times the number of chirps, which we don't know. We just solve for C, and then we're going to multiply our final answer by 4. If we do that, we're going to subtract 30.281 from both sides. We are definitely going to use a calculator. And I'm not going to use a calculator, but let's see if I make a mistake. All right, when we do that, we're going to get 44.719, hopefully. It's going to equal 1.143 times C. And then we're going to divide both sides by that 1.143. All right, and that should give us the number of chirps. Let's round to the nearest chirpage. Or maybe not. I don't know. 44.719 divided by 1.143 is about 39.124. So again, this point should be on our line, right? If that's our input chirps, that should be an output of 75 degrees. And you can see, yeah, this point is on our line. That's good. Anytime we're using our model to make a guess, our guess should lie on the line. If the guess didn't lie on the line, if it looked like this, we must have made a math error. Okay? It always lie on the line. All right, so our final answer is, well, how many are there going to be a minute? That's 15 seconds. Multiply by 4 to get it in a minute. And 39.124 times 4, about 156 chirps in a minute. There we go. That's how we do it. So next up, I want you to try to do the same thing. I want you to try to generate a linear model. Type in this data into Desmos, find your linear model, try to do this problem on your own. Pause the video, go through it, and then we'll go through the problem together and see if we get the same thing, or you can just skip to the end. So save the data from both examples. I should really say both examples. We're going to use both of them later. You can either open up a new tab, or you can create a new table in this tab. I'm going to open up a new tab. This, so I don't have to worry about anything bad. All right, and I'm going to make another table by typing table. I'm going to type in our data. All right, 1994, 113. Oops, not 113 tilde. 1995, 116. All right, it's going to be 1996 next. 118 and 119. 123 and 125. In 2000, it's 126, then 128. In 2002, it's 131 and then 133. In 2004, it's 136. So let's say you made this typo, by the way. This is a good point. Hit the plus mark, and it's going to zoom to show you the data. Now, maybe something happened in 2004 that made these numbers crash. Or maybe there's a typo. And that's an outlier. We haven't talked too much about it. And you always have to kind of ask yourself whether it means something or was like a data entry error. But it should always make you kind of scratch your head if you see it. So we got it. Looks like pretty linear. This data is actually really, really closely correlated. Wow. Looks very much like a law on a line. Not perfectly on a line, but pretty close to on a line. So this is gas consumption. So we have the year. And again, usually for years, if we don't want our inputs to be really big numbers when we're plugging things in, usually for years, we like to do T years since 1994 or something like that. But I want to show that it really is fine and possible to have the year itself be your input. So our input is the year. Let's call that Y. Our output is the consumption of gasoline in billions of gallons. Okay. So I think we got that already. Determine if this trend is linear. Yep, it is. If we had 5 exclamation points for the last one, we need at least 3 more on this one. Find a model for the data. So see if you remember how to do that. Again, these are X1s and Y1s. So we'll go to a new box, type Y1, tab to get out of the subscript is approximated by M times X1. When I say tab to get out of the subscript, this is, oh, actually it works if you don't tab to get out of it. Anyway, there we go. That's our line. It looks like it fits it pretty well. How well does it fit? We'll talk about that in the next video. Anyway, so here we have our line. I wrote it as y equals mx plus b. We could write it as b plus mx. It's the same line. And we can write down our b values and our m values. So we're not going to use y. Our output variable is c. And I'm going to get this right this time. C equals our input variable, our b value. Right, we know it's going to be c equals b plus m times y. Our b value, it says, is negative 4291.61. And our m value is 2.209. That's not the word, 2.209. So again, if we had T or Y be the years since 1994, this number would look a lot prettier. This number is kind of so ugly because we're having our input be the year itself. And our years are really big numbers, but it's fine. So there we go. Yes is our nice box. Yes is our answer to the first one. And this linear model, just a linear equation that models the data, that fits the data, is our answer for the second part of this question. So let's predict consumption in 2008. So our input will be 2008 because our input is just the year itself. And we want to find our output. There's no question mark there. Just find C. Hopefully what you did is you said, well, C is negative 4291.61 plus 2.209 times Y. Y is 2008. You just plug that in to get an approximation. You're going to get negative 4291.61 plus 2.209 times 2008 and get 144.062. I use these squiggly bars to show approximately equal to. It's showing that we're rounding. Although I think in this case, we might not actually be rounding. Oh well. We're going to say about 144. It's gas, but it's not gallons of gas. That would not be very much. Billions of gallons of gas. And now that we're actually after 2008, you could see how good this extrapolation was. It's called an extrapolation because we're going outside of our data to guess. If we wanted to do, well, we have all the data in between, but if we wanted to find something in between the data, that would be like an interpolation. Interpolation, extrapolation. We're not really caring too much about that in this class, though. All right, hopefully you got the same thing. Let me know if you have any questions, and have a good one. Bye-bye.